I'm Tim Ventura, and we're joined today by Mitch Randall, the CEO of Ascendant AI and the innovator behind the SkyWatch Passive Radar UAP tracking system. SkyWatch was developed through the Galileo Project and hopes to detect UAP using reflected signals from existing transmitters as an alternative to traditional radar technology. Mitch has a master's in both electrical engineering and physics and a long history in scientific instrumentation and radar, dating back to 1984. His experience includes roles at the National Center for Atmospheric Research, along with dozens of key inventions in radar technology widely used across industry. He co-founded BINET in the early 90s to bring bistatic 3D velocity measurement to research weather radars all over the world, and co-founded the Advanced Radar Corporation in the early 2000s to commercialize these innovations for applications in the commercial weather radar market. In 2005, he co-founded WildCharge to commercialize wireless charging technology for consumer electronics. In 2018, he co-founded Ascendant AI, and in 2021, he became a research team member of Harvard's Galileo Project, where he developed the proof of concept of a SkyWatch receiver. He is the lead author of the paper describing the SkyWatch receiver for the Galileo Project in the Journal of Astronomical Instrumentation. So, Mitch, welcome. It is a pleasure and an honor to have you with me today. Thank you so much for joining us.
Oh, thank you. I feel honored. I've seen your lineup of people you've interviewed. I'm really honored to be in that lineup.
Well, I mean, you and I talked. I want to get this out there for the audience. So you and I talked the other day, and I absolutely have to bring you back in the future to talk about artificial intelligence, SETI, astrobiology, and humanity's place in the universe. So you have so many brilliant big picture ideas. But when it comes to radar, I mean, again, just reading your intro there, I can't think of anyone who is better suited to approach the UAP topic from a radar perspective. So again, thank you so much.
Oh yeah, I'm happy, and I'm really lucky to have the combination of skills that I do that happen to fit exactly this problem. So that's fortuitous. I actually started talking to Peter Davenport back in the early 2000. I said, hey, I know you're trying to do this passive radar. Well, I know all about bistatic. So we started back then.
Well, so let's get into that. So today we are talking about passive radar for UAP tracking, and we definitely have to break this down for the audience. My thought on this is, when I first heard about it, I didn't understand what it was, and then when I started to kind of do a little bit of reading on it, I was just blown away. I was like, oh my God, this is the smartest idea I have ever seen, right? So the general idea, and again, you said this goes back to Peter Davenport way back when, is radar signals are already out there, right? Electromagnetic signals are already out there in the environment. Instead of sending those out ourselves, which airports and weather stations and things like that may do, we can basically use reflected signals from what's already out there to potentially track UAP, right?
Right. In fact, I mean, you look around, you are basically a bistatic receiver. You're not transmitting light and then receiving it with your eye. You're using light that's already there. We're very familiar with this idea, but when you talk about radar, most people think about what's called monostatic radar. That's the regular radar where a dish spins around. The details are, it transmits a little pulse. The pulse goes out, hits a target, comes back, and you get that reflected signal, so you know something's there, but you can also get that timing, so you know how far away it is. Bistatic radar is really cool because you don't have to actually transmit. There's no reason that you have to be the one who's doing the transmitting. There's already plenty of signals out there, like FM radio stations, digital TV radios, or digital TV stations. There's lots of stuff already out there, and they're transmitting lots of power. So that's something we can take advantage of, and it is a beautiful idea.
Yeah. Well, because again, the FCC severely limits and regulates what is allowed to be broadcast, right? And so in terms of UAP, especially in terms of like a citizen science project, if you wanted to go out there and set up some kind of a radar station for UAP, I mean, at the very least, you would have to go through a ton of regulatory hurdles. And, people may not be aware, but like bandwidth is limited, spectrum is limited. There are all sorts of limits that are in place, right? But when you're using passive, you're just picking up what's already out there. Someone else has gone through all of those regulatory channels. Someone else has basically they're paying the power cost to broadcast. They're dealing with all of the hassles that are involved with it. All you have to do is, I'm guessing, detect their primary signal and then measure reflected returns from anything that might be flying around, right?
That's right. And if you look into the, I mean, there's a lot we can talk about just to all the advantage of this. But one of them is a typical radar, let's say a weather radar, we transmitted a megawatt in this pulse that's 1 microsecond long, and then another millisecond later, we would transmit another one. Well, if you look at that average amount of power that you're transmitting, it's actually, even though the peak power is a megawatt, 1,000,000 watts, the average amount of power that you're transmitting was only about 1,000 watts. So that's, it turns out that sensitivity, when you go through all the equations, what really matters is the average power. So here you have, let's say an FM radio station transmitting 100,000 watts continuously. So it's 100 times as much, than I'm used to with weather radars. And so that's a lot to work with. So the sensitivity of the system is quite good. And there's some other advantages. And I'm really excited to kind of get into some of those details. It's really cool.
Yeah. And I did make notes on a lot of those. There are a lot of different ways that you could take this and evolve it way past even traditional radar. But again, I didn't mean to interrupt. Go ahead, sir.
Oh, well, hopefully we'll interrupt each other a lot more because there's just so much here, I really liked Peter Davenport's paper back in 2000. I think he wrote something in the mid 90s, and it was on his webpage for a while so he's the director of the National UFO Reporting Center, right? And he figured out, who knows how the idea came to him, that this is a great idea. I mean, a big part of it is the government has a monopoly on radar data. We don't get to see radar data. And I really want to get into that because there's plenty of video and plenty of photos, but there's limitations that are really important, and I want to talk about that later. But he figured out, we need radar data. That's how we can really detect UFOs with radar data. But who's going to put a megawatt transmitter on the roof and a 30-foot dish or whatever it takes? A monostatic radar is a big investment. And, then you were just talking about the licensing and whatever bandwidth, all this stuff that you have to worry about just to get that going. But he wrote, in the paper he wrote, I love to read it. It was great. He goes through a history of all the, it's really concise, and I hope that we can put the link on this video.
Oh, absolutely.
Yeah. So you read it and you realize, my God, they've been using passive radar for a long time. And the one that's really interesting is the Space Force's fence radar. And that's been in operation for many years. I think it's been now replaced by something else. But basically it was transmitters, a few transmitters across the United States, kind of all on the same latitude, and several receivers. So there's like 8 receivers all the way from California to the Atlantic coast. And with that system, they could detect anything up to 22,000 miles away in space. So they're looking in space, trying to detect objects and keep track of what's up there. But they could look all the way out to geostationary orbit and get anything within that's 10 centimeters or bigger. So I mean, it's an incredible technology. And like I said, it's not like this was just invented and we're trying to figure out something about it. This is an established thing that works really well.
Let me jump into the UAP side of this, because I did some historical research that I think is just valuable. A lot of folks may already know this, but it's good to kind of get it out there. One of the big questions that people may have is whether UAP are detectable on radar. But surprisingly, it seems, again, looking back over history, that one of the most consistent ways to identify and track UAP is on radar. So if I understand things correctly, radar signatures for UAP date back to the 1950s, and there have been dozens, maybe hundreds of times that interceptor jets were scrambled based on those signals over the years. So radar also forms a significant part of the more current data set from the 2004 Nimitz sightings as well. And I believe there were several different variations on that radar data, right? Like from what I understand, they were getting signals at sea level from the ships, but there were also indications that it set off an anti-ballistic missile warning system. I believe that's also radar, although I might be mistaken. So in terms of tracking UAP, it seems like they do consistently show up on radar. That is kind of one of the most safe, in addition to FLIR and all the visual stuff that has been used.
It's the gold standard. I mean, that's why every aircraft carrier, every aircraft, every military site, anything that wants to have any situational awareness, it's got radar. It's the gold standard. And then, the question whether UAPs can be detected on there. Well, if they can, then we don't know about that, right? Because for one thing, if you can't detect it on radar, the chance you're going to catch it on a camera is way lower. And I would love to talk about that. I don't know if you want to stick that in here now, but
well, let's come back to that, because I think that's
sure.
a really important point. And there are organizations out there looking at 360-degree visual observation platforms. And I had the same concern that you did, right? It is limited range, cloud cover, weather conditions, and time of day obscure those. And so radar, as you've said, this is the gold standard. And the passive radar opens that up for small and scientific projects.
Right. For a crowd, citizen science. Exactly.
So one of the earliest big radar contacts that I read about, again, just setting context for the audience, was between July 12th and 29th, 1952, over Washington, D.C. This was what they called the quote unquote invasion of Washington. And it led UFO historian Curtis Peebles to say, never before or since did Project Blue Book and the Air Force undergo such a tidal wave of UFO reports. So for a period of time over Washington, D.C., everyone had UFO hysteria, and there were radar returns coming in from all over the place. Now, later, the Air Force came back and speculated that it was a temperature inversion causing those reports. What are your thoughts on that? How often does radar get confused?
Well, fun topic, because I think I mentioned to you in our other conversation that temperature inversions and anomalous propagation, they're kind of the swamp gas of radar data. So they can, here you have radar, which is the gold standard, and there's so much you can detect with radar, and it's quantitative, and it's got distance to it, so you can actually get position in space. It's so rich with data that's so definitive, but they can just say, oh, temperature inversion, and then everybody goes, oh, well, it's just fake then, or it's just a mistake. And so, it's kind of feeding off the fact that there's not a lot of radar experts around that know what even that means. So anyway, it's just something they can throw out there. But in the case of swamp gas, people go, wait a minute, I don't even know what that is. And, that sounds kind of fishy. That's what a radar person thinks when the first response is, oh, it's temperature inversion.
Yeah. Well, the reason I mentioned that was actually to set this one up as well. So Philip Klass, a senior editor for Aviation Week magazine, was quoted as telling a reporter, radar technology in 1952 wasn't sophisticated enough to filter out many ordinary objects, such as flocks of birds, weather balloons, or temperature inversions. And he added that the introduction of digital filters in the 1970s led to a steep decline in UFO sightings on radar. For me, this brought up two giant points. First, radar can produce false positives, right? We need to be aware of that. Any kind of instrumentation can produce false positives. And second, and I think more importantly, it seems that UAP have been automatically filtered out of radar systems now for over 40 years.
That could be very likely. And there's some other factors about radar which kind of automatically filter out things. So, suppose I'm just going to throw this in. It's kind of random and kind of sidetracking your question a little bit. But suppose something is going in the atmosphere, suddenly makes a right-hand turn. Okay, that sounds really interesting. But let's say the radar sweeps around. It sees one dot here and it sees another dot here. There's no evidence of that, that right-hand turn. So, a radar that sweeps around and takes seconds to get back is not really the ideal instrument anyway, in that form, to see exactly these kind of anomalous property that we really want to see. But getting to your question, the whole thing about filters is, when that's an important point. These filters do something, and we talked about it when these other balloons and whatever were going over the United States earlier in the spring. They were saying, oh, we don't have our radar tuned to look at some of these objects, and now we're tuning them, and we're starting to see more of these objects. Well, that's a good point. You control the digital filter, so you define what it does. And so if you're not looking for, little objects that are floating at zero velocity, you might put a zero velocity filter out to get rid of all the ground clutter, and it would get rid of all your anomalous objects out there. So that, it's a real thing, and it's a big deal. So when you do design your filter, you got to know what you're trying to filter out and what you think is positive and what you think is negative. So you're exactly right. It's very possible that just the thing we would want to see has been filtered out from that technology. So.
Yeah. Well, and you mentioned the Chinese weather balloons, and I do have a quote here that I at least want to read. It was from General Glenn Van Herk, who said back in February to Reuters, what makes them really hard to detect and track is their size and potentially the shape. He was talking about the Chinese weather balloons, not about UAP. And then he went on to say very, very small objects that produce a very, very low radar cross section are what are difficult to track. And officials later told Reuters that a key change to NORAD's filters is what allowed them to detect objects moving slowly and at different altitudes, but they didn't specify which ones. So again, this goes back to this whole idea of they are looking for specific types of things in the air and could potentially filter out things that they aren't aware of, I guess.
Honestly, we don't even know if that story is true. You know what I mean? We don't know what's going on. We don't have the data in our hands. Talk about a filter. It's going through some kind of government social filter.
If it's okay, I want to get back into passive radar. So
Yeah.
You had told me, again, this current system that you were looking at, envisioned by Peter Davenport back in the day, this is basically made possible for citizen science by modern technology. You've estimated the cost it may be at or even less than $500 to put one of these receivers together, right?
Yep, that's the goal. I don't want to promise it, so I've been very hesitant to say a number there, but I'm definitely trying to keep a 3-digit number.
Yeah.
Yep.
Well, I mean, there are several projects out there. Like one that I'm participating in is the Global Consciousness Project, right, with random number generators, and that's the same way. It costs it costs a few $100s to buy it, but you can host this at home, and then it becomes part of a larger network. And so SkyWatch is exactly the kind of thing that I would participate in. The idea behind it seems like it is so valuable, just being able to take advantage of what's already out there to help contribute to science and help understand what UAP are there. I mean, it seems like a brilliant idea.
Well, can I just jump into like a little pitch here, a little kind of get into, if you wanted, let's say that you only have a certain number of dollars and people aren't going to buy 10 different instruments from 10 places, we're trying to get the biggest bang for the buck. And what we want to do, let's say our goal is, we want to know the answer to this question. Are there objects flying in our skies that we call UFOs, something that does something that we don't think humans can do? So from an instrument, and then by the way, this is my career. I worked with scientists all my career trying to make instruments that measure the stuff they want. And a lot of times they don't even know what instruments those are going to be, but they definitely know what they want to measure. And it was my job to figure out what instrument is going to do the thing they want to do. And they a lot of times didn't even know that was possible, because they're not technologists, they're scientists, they have a certain job to do. And here we are again, we have a certain job to do. We want to know the answer to this question. So what instrument do we need to make that's going to do it? Now, there's a lot of things out there. There's magnetometers, cameras, radiation detectors, audio and infrasonic and ultrasonic, audio. And there, you can list a big list of instruments. And the question is, okay, which one or combination of those are we going to do? It occurs to me, and when we get into it a little bit, you'll see the radar is by far the best single instrument, and I would say most important. Now, maybe I'm biased, but you can decide for yourself. For example, if you have a magnetometer, and I don't want to put down any instrument, that's not my point, but if you have a magnetometer and it has a reading, how are you going to get from there to there's aliens or there's a UFO, UFOs that have unknown technology flying around? So that's an important measurement. Don't discount, networks of magnetometers. So I'm not trying to put anything down, but that's not what I'm looking for. That's not the instrument I'm trying to design. I want to design an instrument that can definitively determine if something is of extraterrestrial origin or not. And so anyway, to me, radar is the answer. You have to be able to locate something. Now, the only contender, in my opinion, for what, well, here, let's back up a little bit, because let's talk about the 5 observables. Now, we've all heard that, and I hope I can get them all right now, but we have low observability. Okay, that could be, silent. It can be, invisible. It could be not on radar, whatever. We have, help me out here. Well, ultrasonic speed without sonic booms. That's one. We have instantaneous acceleration. When you get to instantaneous acceleration, that's a showstopper. We don't know how to do that. We don't have a propulsion system that can go, Mach 2, but then take a right-hand turn. That's not something that we know how to do. It's not even something we can fake. We don't know how to, if somebody said, here, work for Disney, we want you to make a display of something that goes Mach 2 and then turns right, and any way you can, we don't know how to fake it. That's just something that humans don't know how to do. But we're plenty of reports of that happening. So that's what I'm focused on. I want to pick up that. Now, can you pick it up with a magnetometer? No. You go through the list. Can you pick it up with an audio detector? No. There's a big list of instruments you can have. And it boils down to really cameras and radar. You need to be able to, locate that object in 3D space and track out its motion to look for that kind of instantaneous acceleration. You have to make a time function, and we call that kinematic tracks. So if you can sample it fast enough and you can see, little samples of where it's going, and then you see that, oh my God, to go, they went from straight north to straight, east, in 0.1 seconds, that's X amount of acceleration. So that's what you need. If you use cameras inherently have a problem. So I'm diving into this whole thing about cameras, and I hope this is the right time to do it.
Yeah, no, that's great.
Cameras, the big issue with cameras, and you saw it with the Mosul balloon or Mosul sphere, let's say, we don't know how far away it was. We know it was somewhere between the airplane and the ground, because we know it wasn't underground and it wasn't on the other side of the airplane, but you're done there. You don't know where the distance at all. That lack of knowing distance is critical, because without knowing distance, you can't place something in 3D space. You don't know where it is in 3D space. You just know where it is in the angle of the camera. And so therefore you can't get a velocity, you can't get a position, and you can't get an acceleration. So what can you prove? How can you write a paper based on that? You can't say it was X acceleration and humans don't know how to do it, therefore this is, what are the hypotheses that support this, and you can't get there. The only way you can do it with cameras is to have multiple cameras and start doing triangulation. And that's a perfectly feasible or perfectly doable. We know how to take two cameras and look at the same area with some baseline between those cameras. And then you can do triangulation to figure out, oh, this one saw it here, this one saw it there. They intersect at this point, and that locates the object in 3D space. So it turns out, though, that now I just thought of another thing I really want to throw out there. So don't let me forget about the volume here, but this is perfect to go into the volume. So the issue with that is, another issue with cameras is you can't see more than about 10 kilometers with the camera. Now, if something is a bright light, you can maybe see that very far away, but not everything is a bright light. Like a daylight UFO sighting, it's not a bright light. It's just something in your image that you're looking at. Those kind of things disappear at about 10 kilometers in a regular camera. Or, and by the way, I'm kind of already calibrated. Of course, you can have a telescopic lens and you can see much further, but that's not something you can scan the sky with. So what
and to jump in, one of the things that I've seen, this is from UFO videos online, but there have been some videos that have been posted where the person will post it and say, look, I saw a UFO flying over, I'm thinking of Southern California in this case. Somebody else looked at it and said, no, you're tracking an insect in front of the lens, right? So
exactly.
The challenge with cameras is what you don't know, as well as, I mean, to me, it seems like there's very easy potential for fakery there, right? We see a lot of fake videos going up online. People know how to do that. That's something that's easily and often faked. People are using CGI. There's a ton of potential for mistakes. And so there's just so much wiggle room there that it makes it very difficult. And then on top of that, if you're able to add in photos with radar, right? If you're able to bring that radar in, then you've got a dual data set that reinforces itself. So,
don't let me forget. I want to talk about the app that goes with SkyWatch. It's really awesome, and we can't forget about that. But you just hit on the biggest thing, and I'm going to take everything that you just said and kind of lump it all into the same category, which is you don't have distance. That's why it can be a bug. That's why there's so much debate. When you see a video come out, there's so much debate about what it could be. Remember, I don't know if if you followed in detail, for example, the Tic Tac video, the Go Fast video, everything about that had to do with distance. And the people that got the closest at figuring out what they were seeing actually tried to figure out what the distances are. But there's no way to really know for sure. There's just ways to guess. Because cameras don't give you that. And those debates will go on forever. They'll never stop having that debate. And I've seen, do you remember the Utah video is a great example of this. So it was, and I can't remember the name of the town, but it was a film crew using a drone to do B-roll, and in the background, an object comes and then flies past it, and they estimated that it probably traveled so many miles, and that when it flew past the camera, they estimated it was like Mach 5. So the whole issue with that is some people claim that it was just a little thing of cottonwood floating around and the drone flew by it.
Yeah.
There's no way to tell, and that debate will never stop. There's no way without distance, and you can't get distance with a camera or a single camera. You can definitely get that angle, and you can see stuff that looks cool, but you cannot get that distance, and you're stuck. So I'm just taking what you said, and I'm just really putting an exclamation point on it. We'll never be done with camera pictures because you don't have distance. So that's why I was telling you about the only way to really effectively use camera for quantitative scientific measurement is to triangulate. That's the only way that you can. If you had two cameras and one of them has a little thing that goes by it, but the other one doesn't see it, that was a bug.
Well, and again, to me, this goes back to what I would call the he said, she said debate, right? I mean, what we've seen for 75 years now is someone will come up with a piece of evidence, and then the other side says, oh, no, here are 20 or 30 different reasons why this isn't true. And they don't even have to disprove it. They just have to put enough doubt out there to confuse people, right? And so what made the Nimitz sightings so unique was you had credibility and quality of data that
Yeah.
was finally beyond what the skeptics could easily brush away. And what you're talking about is the same thing. It's
Yeah.
credibility and quality of data.
Yep. And you know, some data inherently doesn't have enough to qualify as, you know, convincing proof anyway. So even if you had a clear video of something, sometimes that's not good enough. You really do need to have triangulation or something that gives you distance so you can get quantitatively back to where you need to be. So, you know, I was trying to map out this whole kind of design process of, you know, there's a need out there. What kind of instrument, you know, are we going to put together? So let me get back on that track, because
Yeah, please, please.
I want to really kind of point out that the SkyWatch concept, you know, inspired by Peter Davenport, he was dead on. The SkyWatch concept is like also the gold standard, and it's really something I think society absolutely needs. So then again, I was talking about, if you want to get anything out of cameras, you have to do triangulation. And I was explaining that a useful camera has to be an all sky camera, because you can't have a total telephoto lens, because you need to have some kind of array of telephoto lens that sees the whole sky. Otherwise, what are the chances that, you know, UFO is going to fly right between, you know, in your viewfinder of a telephoto zoomed in lens? So you need to have like some kind of array of cameras, typically 5 to 7 cameras that point in every direction with maybe a 50-degree beam width, or, you know, field of view. And that's typical kind of thing that we do for, you know, asteroids, and the Galileo Project has an instrument very similar to that. And in that case, again, the useful range of that is about 10 kilometers if something doesn't have a light. If it's a light, way further. But if it's let's say a daylight sighting, 10 kilometers. So then if you want to triangulate, you need to have 2 of these systems next to each other. You know, let's say a 1 or 2 kilometer baseline between the 2, so that when something comes by, they both can see it, and that's all fine. But I want to talk about something also really important in this, you know, instrument design space, and that is, in fact, I was involved with the Doppler on wheels storm chasing radar trucks. Those have been on TV, so you might be somewhat familiar with those. But the idea is, you know, I worked at the National Center for Atmospheric Research, and we had really high-end, top quality radars. That's what we built for scientific study of weather. The problem with it is you have that set up, you know, and one of our radars was on a concrete pad here in Boulder, Colorado. What are the chances a tornado is going to come right by the radar so you can study it? You've got this problem that you have. It's like the drunk who loses the keys, and he's under the streetlight looking for him, and somebody says, you know, why are you looking there? And he said, well, because I can't look over there where I dropped him. You know, this is the only place I can see. So the same kind of thing, like if you have some really great suite of instruments, but they're set up in a place and it has a limited volume that it can see, that's an issue, because we don't want to wait 100 years for a UFO to finally fly through that volume so that you can get a measurement on it. So with the Doppler on wheels trucks, storm chasing trucks, it's a radar that's mounted on a truck, and they have walkie-talkies, and they say, where's the storm? And then they drive 200 miles right to the storm, and then they pick up a tornado. That's the kind of thing you need to be effective with your scientific instrument. So that's the idea. In fact, I'll go into this a little bit too. Jacques Vallée, in one of his books, has a great little paper, and it shows a graph. And the graph is the sight distance, so the seeing distance, versus the number of sightings. So they took some database, I'm not sure where the data came from, but the number of sightings versus the number of the sight distance. And then it, on the graph, and the graph is kind of the steep curve. On the graph, it had ideal. And so, when the first time I saw it, I was like, what do you mean ideal? What are you talking about? The ideal? The answer was that curve was just the volume that the person is looking in. So when if you can see 10 miles, that's the volume 4 pi r cubed. But if you can see 100 miles, that's 4 pi r cubed. Now r just went up by a factor of 10, but it's cubed. that volume just went up by a factor of 1,000. So if you
Okay.
can see 10 miles, your chance of seeing a UFO fly through there is one thing. If you can see 100 miles, the chance is 1,000 times greater that something is going to fly through that area. So this is all about volume. It's all about getting statistics up. So, again, like I'm an instrument design guy. I know that in my heart, that's an important concept. So I don't want to just have a radar that's, some scientist can buy and stick in, Maine or whatever, and then wait for a UFO to show up there. This has got to be something that can be distributed to get the volume way, way up, so that no
Yeah.
matter, when something flies over, let's say, continental United States, there's a radar there picking it up. That's the concept here. And
Well,
and back to that camera thing, sorry, but just to put this last point on there, cameras can do what we're trying to do with this radar, except for you'd need like a factor of 10 times as many. So I think I figured out that SkyWatch network, if it had about 10,000 participants across the nation, we would have full coverage. And multiple full coverage, so that if an object flies by, multiple radars would pick it up. If you wanted to do the same thing with cameras, it would take about 1,000,000 cameras. So that's a very different scale.
you're talking about coverage, being able to cover the entire United States. But then another aspect of that is being able to take that overlapping coverage and provide higher resolution, right? And when you have multiple devices feeding back in, not only can you see the same, hopefully, the same return from different angles from different devices, but you can see with greater resolution and perhaps more detail, I guess.
Exactly. Well, I mean, exactly. Like if there's anomalous propagation, that's a very geometric thing. Like if you have anomalous propagation, that means you're looking in a certain direction, but it's not right in front of you. There's something maybe over the horizon, which is, being channeled by some atmospheric inversion or whatever, but it's very geometric. So the chance of having multiple radars come look from different angles, seeing the same object that could possibly be an anomalous propagation to the east and anomalous propagation to the north, and they all line up on the same thing, is just minuscule. So you can immediately eliminate several things by having this redundancy of multiple radars seeing the same thing. And I've even designed SkyWatch. The kind of grid spacing is 20 to 30 kilometers, but each radar can see 150 kilometers, 200 kilometers. So there's plenty of overlap for lots of radars to see the same thing, and there'll be no ambiguity about what's being seen. There'll be no argument that it's anomalous propagation or temperature inversion, et cetera.
Yeah, well, and being able to bring together all of that data, right?
Yep.
And for me, that's the holy grail is, not just being able to collect the data, not just having one person be able to say, "Oh, look, I saw something here, my radar caught it here," but being able to bring that back to a centralized point. And number one, you're automatically generating UAP reports. Potentially, you're able to cross correlate those, right, with aircraft flight patterns and
Yes.
known objects, and I can't help but wonder if a national network for something like that was in place. That's something that potentially the government or weather stations or universities could tap into as well, right? I mean, like right now we have a government that has apparently an issue with Chinese spy balloons. It would be really nice if they could tap into a reflection network like this and say, look, not only do we have our defense radars looking for these things, but we're able to cross correlate it with this other, open source network as well.
Absolutely. I mean, I think, not only could we help the government with disclosure, but if they were resisting, that would be we would be right there. Like, hey, what just happened? We all saw it. And it wouldn't just be one person or one group. It would be everybody who's in the network. And the way it works, by the way, is the data is collected and put together to make a radar map. So there'd be a radar map of the United States, and it would show what's going on as far as anomalous activity going on. You'd be able to go to a website and you'd see it there, everybody in real time. This isn't something that would, go into a black hole and, some scientists churn on it for 2 years and then write a paper and some minuscule, off some, whatever. It's not, it's right in your face. So we would all see that. We'd all wonder, what was that? And, it gets really hard. This is, the whole idea of distributed technologies rather than
Yeah.
these silos of where as soon as you have any kind of centralized organization, it's immediately open to corruption, immediately open to, changing the messaging and the narrative and everything. But when it's a distributed network where everybody has an open ledger, basically, of all this data, that's a different story. That's
Well,
where
and
this is headed.
we're seeing all these technologies move forward. Like in terms of distributed networks, mesh
Yep.
networks are incredibly common now, right? I mean,
Yep.
people use them for Wi-Fi. So this is something that we see on a daily basis. They're well understood, easily constructed now. The other thing that this reminds me of in some ways is last year, about 2 years ago, I bought a Tesla Model 3. When gas hit $6 a gallon, I said, that's it, right? And in past cars I've had, they use sonar, right? Those little bumps on the bumper where they project the sonar beam out, and usually you have like a backup alarm, right? You get too close and you get like a beep and it says stop and you hit the brakes.
Yeah.
Well, the Tesla takes that to another level. It actually uses those sonar beams to visualize what's around you. And it does make mistakes. It's trying to match what that sonar picks up with known pictures, right? So like it thinks that my garage is a semi truck sometimes, but for the most part, it is very accurate, especially in terms of spacing and size of what's there. And
Yeah.
the other day I was driving down the freeway, and it told me, I was talking to my daughter, and I see on the screen, it showed two semi trucks, one after the other with a car between them. And I thought, well, what's going on here? I look over, sure enough, that's what it was. And I'm like, okay, so I'm traveling at like 65 miles an hour. These vehicles are traveling slightly faster than me. They were passing me, right, in the fast lane. And I'm like, this sonar system is able to not only detect and identify that there's three vehicles, it's able to get the spacing between them correct. And I was like, this is so remarkable. And that is just one vehicle computer. If you were able to put this back into a central database, Lord only knows what you'd be able to do with it, but it would be absolutely remarkable.
Well, essentially what we're talking about here is you're taking all that data into a centralized database. And you touched on something a little bit earlier too, where, we can easily see airplanes. They're all over the place, and
Yeah.
you can see them. And so and they also know exactly where they are. They all have GPS, and they're all transmitting that on a transponder called ADS-B. There's a system for that so that other airplanes and airports can see exactly where the airplane thinks it is. So that's really easy to receive at each one of these sites. Let's suppose this is all over the nation. Each receiver site will be equipped with one of these ADS-B receivers. That means that we know exactly where these objects are in the sky, but we're also seeing them in the radar. So that's calibration right in your pocket. So when the system figures out where that dot is in space, it can correlate that with what the airplane is transmitting, where it's at. And therefore, this thing will be calibrated continuously. If something flies by and we determine, hey, that's a weird object, what's that doing? And it has no transponder, coming out of it. So it does, let's say, a right angle turn or something. There's not going to be any question that the system is calibrated, because it's basically being continuously calibrated in real time all the time. So there's some beauty to the system that's just so wonderful how it all worked out. And I have to say this. Here's a system that, like I said, that this is my job. I'm an instrument designer, and I came up with this concept, figured out all the details. So it's a fully worked out engineering concept. And here we are. We could have this. This is what you call a shovel-ready project. This is not something that has some pie in the sky, big research that has to be done, or we don't know this or we don't know. No, we know everything about this. This is this established technology. There's a design in place. It's ready to be made. And the question is society, is there Is there an appetite out there? Does society want this? Because if they do, we can fund this and we'll have it. That's all we're talking about.
Well, I see this as part of a new generation of activism, right? I mean,
Yeah.
activism in the past, and it still is, it's about making your voice heard. It's about sharing your opinions and persuading others, letting people know about the issues. But this is scientific activism where people are out there helping, right? It's not just talking, it's doing. And yeah, I mean, again, this is something I would love to participate in, and I could probably think of at least 20 people offhand that I could call who would just start jumping up and down if one of these things was available. So I want to ask about the availability. Is SkyWatch, is this something that you're going to start selling as kits, or are you going to give away plans or open source model for it?
Yeah, let's talk about that. So although the concepts are all in place, the work has to be done, right? And that's a team of engineers and programmers doing that work. And that's, we can't ask people to quit their jobs and work on this for free. So that needs to be funded. There needs to be, like, for example, the antenna that goes on the roof needs to be designed and the details worked out in that. There has to be, I mean, a huge part of this is when you put 10,000 things out there, these are consumer electronic products now. This is no longer a scientific instrument. This is a consumer electronic product because, somebody who knows how to install a printer should be able to take this thing and install this thing. So it shouldn't be something that you have to have a PhD in or whatever. It's plug and play. You should be able to figure out how to do it. And then the cost has to be down. So to get a product to the point where the cost is low and all those kind of things have been worked out to make it plug and play, that's a significant development effort. So that's the thing that needs to happen between now and when this becomes available. And we just need funding for that. And another thing I'd like to just add in there is we've explored the idea of crowdfunding. And a lot of people have suggested, just do crowdfunding, put it on a Kickstarter or Indiegogo or something like that. Those, unfortunately, we feel the model isn't right for those for a couple of reasons. One is when we do sell these, it's going to be roughly not that much over cost because we have to keep the cost down in order to get it to be proliferated. It's a radar. Yeah. There is some technology in there, but it's not a cell phone. So we can't build our own chips. We don't have that kind of budget to really bring the cost down by that kind of, specialized integrated circuits or whatever it would take to do that. We have to use off the shelf, components and whatever but to get the package to a price that people can actually afford and install. So that's a big task. And then the other thing is we're not trying to become billionaires. We're not trying to start a company. This isn't the thing where the founders can all, suck it in and eat ramen noodles for 2 years, because we're going to get some kind of big back end payoff. That's not happening here. This is I have a team ready to go, a team of professionals. These are people who, build stuff, scientific instruments and consumer electronic products and mechanical engineering designs and whatever. They have to be paid. That has to work that way. But there's not going to be some big profit thing at the end. When this is done, there's going to be data. This is a passion project. We want to solve this problem. There's no way we can make money off the solution to this problem. All we can do is get the instrument out there so that society has the answer to this problem. So it doesn't really fit into the kind of Kickstarter thing because, a lot of times for one thing, they'll sell the product that they're kickstarting at some discount. We can't really do that. Our whole product's going to be a discount. There's never a time when it's not going to be a discount. So, we're kind of basically we're just looking for, angel funding, or it's not even really angel funding. This is donors. We're looking for philanthropists who want to see this problem solved. And, that's whether that happens or not, I don't know. And I really can't get too emotionally involved in that because, maybe no one will step forward.
Yeah, no, that absolutely makes sense.
If they do, here we are. I've got the team assembled. We're ready to make it. We're ready to solve this problem. And the other thing is I was kind of touching on earlier is we can help the government move along on disclosure because we don't know what they're going to do. If you're following this whole subject, it always sounds like next month it's going to happen. but then somehow next month always gets derailed. That could go on for 20 years. We have no idea. So this can definitely help things along. But more than that, let's say that disclosure does happen. In my opinion, this is absolutely essential to verify. So there's this whole thing about trust but verify that we did with nuclear weapons and everything. I think we need to do the same thing here. Let's say the government says, aliens are here, they're nice, and but they're not flying around, but they just come to this base over here or whatever. Whatever their story is, how do we know that's true? We've been lied to for 75 years.
And that gets into and again, we should definitely do more. We should definitely do more talks in the future, because now what you're getting into there is a whole nother rabbit hole. And the reason is the UAP phenomena itself appears to be relatively benign, and yet we have decades of reports of abductions. We have unexplained cattle mutilations. There are a lot of strange things that appear to be associated with this, right? Some of that may be psychological. Some of it definitely is leaving physical evidence, and it's enough to make us wary. So a tool like this would let us help basically expand our knowledge of everything that is going on, right?
Yeah, we need to know what's going on, and we can't wait for somebody to tell us what's going on. We have to just do it.
And I don't think that the government, I mean, again, I think all of us as Americans, we tend to think of the government as a big monolithic entity, and it's not. But even in terms of the Department of Defense or the military, the organizations that are tasked with protecting us, I don't think that they have a handle on this. It's outside of their jurisdiction. It's outside of what they were designed to do. And UAP has been an exception for them to their processes for 75 years. So if they don't know, they're not set up for it. Someone has to find out, right?
Yeah, Tim, before I go, I definitely want to tell you about the app that goes along with SkyWatch.
Yeah, please.
Because it's very, very cool what happens. But suppose that because there's the network radars, that there's some object going across the country at Mach 8 making zigzag motions or something like that. There's no reason that we can't send a signal to somebody who has an app and say, run outside, look to your northeast, because there should be something pretty interesting in about 14 seconds. So imagine, actually, I've talked to a number of people. I talked to someone just the other day that said he was outside taking pictures, and then he put his phone in his pocket, and then he saw an anomalous object, and he never thought to get his camera back out and look at it again. And I know how that works. Like when you see something that's unusual like that, you don't want to pull out your phone and start fumbling for anything. But imagine if you're already ready with your phone, and there's, you've been told something's coming your way, you can run out there and measure it. And if we have multiple, obviously we'll have the radar data for that, but like you were saying earlier in the conversation, if you had an image of that, wow, that would be really compelling.
Well,
More so if you had a couple cameras on the same one, then you could have optical triangulation in addition to the radar data. So it would be completely different. They call it multi-sensor data. Wow.
I think wow is the right word, because those images would be supporting data, right?
That's
and that would also help go against this claim that, oh, it's an insect, or oh, this is CGI fakery. You say, well, no, the device told me to look here. I looked here. I got these photos or this video. This is what it is. So, and as you've said, you might potentially have 2 or 3 different people in that area getting the same thing from different angles. So
right. I've thought about this a lot, because what is disclosure? We have David Grush come out. He said a bunch of stuff. In my mind, that was disclosure. we were almost there. But what I figured out is what disclosure really is what it really is an agreement that something happened. An agreement. It's when there's no controversy. And the New York Times reports it, and the president can talk about it. There's no controversy. That's when it's disclosure. But if you have a system like this, I claim, and I think I can argue this, that this would bring about disclosure. Because if you had 10,000 people with 10,000 radar receivers and this data that's calibrated constantly, and you see something that has that the only hypothesis that fits it is non-human, machinery. I believe that you're in a zone where that's citizen disclosure, and you can there's no controversy. How could somebody say, well, let's hear what the debunkers say? I mean, when it's video or photographs, and we're all used to that, the debunking will never stop. And there's no way, for the person with the photograph, the person who's not the debunker, to get anything out of that picture or that video, because you don't know distance, you don't know acceleration, you can't, you're limited. Maybe it was a bug that just went in front of your camera. You don't know. Maybe it was CGI. But you get 10,000 radar receivers that see something go across the country with videos from people all across the country, and it's making zigzag motions with 1500 G turns or something like that. We're there, I think.
Yeah.
So
Mitch,
that's what this brings, and that's again, it's shovel ready, and it brings that. So I'm just crossing my fingers that society has the appetite for it, wants to come forward.
on that note, let me close for today. It has been truly a pleasure and an honor speaking with you. Absolutely wonderful. Again, this idea, I am, figuratively speaking, jumping up and down in my chair. This is one of the most exciting ideas in terms of technology that I have seen in a very long time. So thank you so much. Let me close by asking, what comes next for you in the next few months with SkyWatch? What can we expect to see?
With SkyWatch, I'm just doing my job, trying to get the word out there. And again, like, I can really do nothing other than wait and see if somebody thinks, or some group of people think, that this is worth funding. So unfortunately, there's no way I can make that happen other than just getting the message out there and hoping people realize this is a good investment. This is a good thing to get the answer we're looking for.
Mitch, thank you again so much for your time today, sir.
I'm so honored. Thank you so much. I really appreciate it.